Okay, today we're going to discuss fluid flow. So far in our discussion of fluids, we've been thinking of fluids as static or not moving. But today we're going to start to consider what's going on when a fluid is in motion. And throughout this lesson, what we want to be thinking about is what are some ways we can describe the speed, the flow, or the movement of a liquid or a gas. And we talked about this last time, but just as a quick reminder, an ideal fluid will meet the following criteria, which is that it will be incompressible, so density doesn't change as we change the pressure around it, and it's not viscous, so it doesn't exhibit any internal resistance to its flow. So let's think about the shapes and paths that a fluid will flow through as it flows. So a flow tube is a volume through which a fluid flows, and we can see a flow tube over here in the top right. And you can think about like if you turn on a garden hose, right? Then the water will come out of the hose, and it'll kind of make a shape along which all that volume of water follows as it makes its path to the ground, right? And that's essentially just a flow tube. It's the volume through which the water or the fluid is flowing. And sometimes is created by a physical barrier, right? As water flows through the hose acts as a physical barrier to keep it flowing. But then even once water comes out of a hose, it still kind of follows a volume that it moves through, right? Even if there's not a physical barrier around it. So that's what we call its flow tube. And within that flow tube, it'll follow flow lines. And flow lines are just the paths of motion for the particles in a flowing fluid. Now, in many flow tubes, they'll all flow in a straight line, like when you're moving through a garden hose. However, sometimes it's moving through different volumes of space, right? So down here in A, we're going from a large volume into a small volume. And so you'll see that those paths that the water follows through kind of converge as they go from the larger volume into the smaller volume. Or if we take a look at this aerofoil over on the right side, and we're going to talk a lot more about this next class when we discuss Bernoulli's principle, but the air will flow around an aerofoil, which is just the shape of a wing. You know, it's this teardrop shape, looks like the wing of a plane or something like that, or the wing of a bird. And the air will flow around it. And again, it'll make flow lines. And as it flows around that object, we'll get those nice flow lines. Okay, so these are just the paths that the particle and the fluid move through as they flow. The flow of a fluid can be said to be quote unquote streamlined when the velocity of any arbitrary particle of that fluid is tangent to a flow line. So the ideal case of this is what we call laminar flow, which is where all those particles move in a straight line, and those straight lines are all parallel to each other, and none of those particles cross paths. The opposite of this is what we would call turbulent flow. And you'll notice in that picture where all of the particles are kind of intermingling their paths. They might be bumping into one another and they're intersecting one another's paths. So laminar flow describes smooth motion of a fluid. And we can see in this smokestack over here to the right, down the bottom half, there is a very smooth flow, and those particles of the smoke are kind of moving in what we would call lamina or sheets next to each other. So the particles are staying in their lanes as they go. Each particle can be in one lane, another particle is next to it, but they are not intermingling or intersecting. However, the turbulent flow up on the top, all those particles are bumping into each other and they're moving around through and intersecting with each other's paths. And that's why we would call this turbulent flow. All right, so let's take a look at a cool example of laminar flow right here. This fluid you can see as laminar flow because it is flowing so smoothly that the camera doesn't even capture the movement of the liquid, right? The same thing can be said for this hose, this water right here. It looks like it's almost still until you put your hand through it, and then you see there is motion of those particles. So these are examples of laminar flow that is so perfect. The flow lines are so well followed by the particles that it doesn't even look like the particles are in motion at all. All right, so let's start thinking about how to measure this flow. So, what we're first going to do is we're going to think about volume of a fluid flowing over time. So, when we represent this with a metric or a variable called volume flow rate, which we represent with the letter Q, capital Q. So, this describes the volume of a fluid that's flowing through a particular location per unit time. And so big Q equals volume flow rate and equals volume over time. And we've got this picture down here. So if we think about this volume of fluid represented by the cylinder, it's going to be moving through space. And if we look at any point, for instance, right here, over some amount of time, there's going to be some length of fluid within this cross-sectional area that passes through it. And so that volume per unit time is what we call our flow rate, or Q. Volume in this case is measured in meters cubed, are our standard units here for volume. Time is measured in seconds, and then flow rate then would be measured in meters cubed per second. All right, so let's do a quick example problem for volume flow rate. We have our equation up here. Our Q, or our volume flow rate, equals volume per unit time, V over T. Let's figure out how many cubic meters of blood the heart pumps in a 75-year lifetime, assuming the average flow rate is 5 liters per minute. So we've got our average flow rate equals 5 liters per minute. And we know that our time is 75 years. So let's get both those into units that we want and that are compatible with one another. So first one, so we've got our flow rate is 5 liters per minute. So let's get our number of years into minutes. So we can take, and we know that every 1 year has 365.25 days, and every 1 day has 24 hours, and 1 hour has 60 minutes. So if we multiply across the top, divide across the bottom, we can get our number of minutes that are in 75 years, because we've canceled out years, we've canceled out days, canceled out hours. All that we're left with is minutes. And that's 39,447 minutes, or 3.9447 times 10 to the 7th minutes. So now that's compatible with the minutes in our flow rate, but we also want to figure out, we're trying to figure out cubic meters here, right? So for every 1 liter, we want to figure out how many meters cubed there are. Well, let's figure out something that we do know, which is we know that for every 1 centimeter cubed, we have 1 milliliter, right? So let's go to milliliters first, and then centimeters cubed, and then we can get to meters cubed. So for every 1 liter, we have 1,000 milliliters. For every 1 milliliter, we have 1 centimeter cubed. And we know there's 100 centimeters in every 1 meter. But that means we got to cube that, right, to figure out how many centimeters cubed there are in 1 cubic meter. And so what we'll be doing is taking 1,000 ml, 1,000 milliliters, right? There's 1 milliliter per centimeters cubed. And then right here, 100 cubed is going to be 1 million. So there's 1 million centimeters cubed in every cubic meters. So we're be taking, multiplying by 1,000, dividing by a million. So this will end up being 0.005 cubic meters per minute. And finally, let's combine those variables we have. So we know that our flow rate is going to equal our volume over time. But if we want to solve for volume, that's our flow rate times time. In this case, we've got 0.005 cubic meters per minute times 75 years in minutes, which is 3.9447 times 10 to the 7th minutes. And that ends up being 2 times 10 to the 5th cubic meters. All right, so we've got our volume flow rate. Again, we described that with Q equals V over T. We can also describe this flow rate by incorporating velocity of individual particles or areas of fluid as they move through our flow tube. So our volume, we know, is going to be our area, our cross-sectional area of that flow tube, times the distance that any individual particle is going to move over that interval of time that we're looking at. And that's what will give us this volume that we're looking at right here, right? So if we pull out that A, we can take our area and multiply that times distance over time, the distance that any individual particle will move while that volume of fluid moves by that point that we're judging everything by. And of course, distance over time, we know is velocity. So we can get our average velocity of our particles moving through this flow tube times the area, and that should be equal to our volume over time or our volume flow rate. And just as a quick reminder, area is that cross-sectional area of the flow tube, the flow of the fluid particles, and that's measured in meters squared. And velocity is our average. That's why we've got a little bar over it. Our average velocity of the fluid particles as they move through this flow tube. And so now we can set up a bigger equation here. So Q is our volume fluid flow that equals volume over time, or area, cross-sectional area of the flow tube times the average velocity of those particles moving through the flow tube. So let's do a quick example problem. The good water fountain down in the lobby has a spout with a radius of 0.5 centimeters. If the particles of water come out of the spout with an average velocity of 1.27 meters per second, we should be able to figure out the volume flow rate of the water in the water fountain in terms of meters cubed per second. So let's think about what we know. So we know that our average velocity is 1.27 meters per second. We know that our radius is 0.005 meters. And we can find our area because our area is pi r squared. So our cross-sectional area for that water fountain will be pi r squared, which is pi times 0.005 meters squared, which equals 7.854 times 10 to the negative fifth meters squared. So to find our volume over time, our volume flow rate equals volume over time, which also equals our area times our velocity, right? So if we take that cross-sectional area, the 7.854 times 10 to the negative fifth meters squared, and if we multiply that times our velocity, which is 1.27 meters per second, we end up with meters squared times meters and meters cubed over seconds, and we end up with a volume flow rate of about 0.997 times 10 to the negative fourth, or about 1.0 times 10 to the negative fourth meters cubed per second. Okay, so we know our volume flow rate. Let's figure out how long it will take to fill up a certain volume. In this case, a 2-liter soda bottle. So we just talked about how if we have 2 liters, if our volume we're looking to fill up is 2 liters, we know that every 1 liter is 0.001 meters cubed. And so 2 liters is 0.002 cubic meters. And if we've got our Q equals volume divided by time, if we want to find the amount of time that it takes to fill up a certain volume, we can take our volume divided by our Q, and that should give us the amount of time it will take to fill up that amount of volume at that volume flow rate. So we've got our V over T is our Q, and we've got our volume. Our volume is 0.002 meters cubed. We're going to divide that by our Q, or our flow rate, which is 1.0 times 10 to the negative fourth meters cubed per second. If we divide by 10 to the negative fourth, it's the same thing as multiplying times 10 to the fourth. So if we take 0.002 times 10 to the fourth, this should be about 20. And then meters cubed cancel out with the meters cubed, and the seconds end up in the numerator. So this will take about 20 seconds to fill up a 2-liter soda bottle. All right, one more way to describe the flow of a fluid, and this is one we won't use terribly often, but we talked about volume flow rate. We can also describe the flow rate in terms of the mass that is passing through any individual point within this flow tube per unit time. And the way that we represent this symbolically is m with a little dot over it stands for the mass flow rate. And this will be measured in kilograms per second. So that m dot equals mass over time. And since we already had our Q, we know that Q is volume over time. All we need to do is multiply that times density. And that gives us, since mass times volume since density times volume is our mass, that gives us our mass flow rate. So this is equal to density times area times distance over time. And this we can convert back into velocity because we know that, again, distance over time is velocity. So our mass flow rate over time, we can relate that to the velocity of any individual particle moving through our flow tube as density, or rho, times A, the cross-sectional area of the flow tube, times velocity, the velocity of the individual particles. And let's put this into the water fountain problem. So remember that we found a flow rate, a volume flow rate for our water fountain of 1.0 times 10 to the negative fourth meters cubed per second. So let's try to figure out what our mass flow rate would be. And in order to find our mass flow rate, we just need to take our flow rate, which is V over T, right, and multiply that times the density. And remember that the density of water is 1,000 kilograms for every meter cubed. So if we convert this into mass flow rate, our mass flow rate is going to equal 1,000 times 1.0 times 10 to the negative fourth, or 0.10 kilograms per second. So again, we won't use mass flow rate too often in here. There's something to keep in mind if you continue further on and you look at more at fluid dynamics and the movement of fluid further on in your chemistry or your physics or your engineering careers. Okay, last piece of the puzzle here. Let's talk about something we call the continuity equation, which we just talked about the mass flow for a fluid. And that mass of a moving fluid doesn't change as it flows, right? So if we think about this mass of fluid right here, its mass will not change as it's moving through this tube, which has a large cross-sectional area, and won't change as it continues moving and eventually passes through this tube, which has a smaller cross-sectional area. And if we're talking about an ideal fluid, then its density won't change either. Because remember, we said an ideal fluid is incompressible. Now, most liquids aren't exactly ideal, but they'll act pretty close to an ideal fluid. However, these principles will not hold up for gases, right? Because gases will expand to fill the volume of their container, so they won't behave very closely to what we're going to discuss right here, right? But the mass flow and the volume flow of a continuous fluid will be constant if we have an ideal fluid or something that behaves similarly or close enough to an ideal fluid. It'll be constant as it moves through its whole vessel. So no matter what's happening with the cross-sectional area of that vessel, like going from this large cross-sectional area to this smaller one, that mass flow and that volume flow rate will be the same. And because of this continuous volume flow rate for an ideal fluid throughout a fluid's passage through an enclosed space, like what we see down this diagram below, we can relate the velocity of particles at any one point to the velocity of those particles at any other point in this fluid's motion by comparing the areas of the flow tube. So again, if we think about some unit time, there will be the same volume moving through the tube at any point in time, right? So right here, this volume right here will move through this tube at the same amount of time as this volume, which is the same volume, will move through this tube in the same amount of time, even though the distance over on the left, D1, is going to be smaller than the distance over on the right, D2. So any individual particle over in volume one over here is going to be moving less fast. So its volume one, its velocity at point one over there will be moving less fast than its velocity over here, which will have to be bigger because every particle is crossing a larger distance per unit time. So if we take and we look at the math here, we know their flow rate at 0.1 is going to equal our flow rate, or Q, our volume flow rate at 0.2, right? This point being 0.1 and this point being 0.2. And since we know that our flow rate is volume over time, our volume of liquid flowing through zero point 0.1 per unit time will equal our volume of liquid flowing through 0.2 per unit time. And we can break down our volume into the area, the cross-sectional area of that tube over 0.1 times the distance that that volume of fluid moves through. And that's going to, per unit time, and that's going to be equal to our area over at 0.2 times the distance over 0.2 per unit time. And of course, we can take and we can separate out our distances over time from our areas. And as we know, distance over time is the same as velocity. So the velocity of those individual particles at point one times the area, the cross-sectional area of tube one, will equal the velocity of those particles in tube two times the cross-sectional area of tube two. And this we can find, unlike any of the equations we've talked about so far, we can find on our AP table of information that we can use on the AP test. And this, again, only holds up for a non-compressible fluid, or an ideal fluid, or one that will not change density as it moves through this through the passage it's going through. However, if we wanted to generalize this for a non-ideal or a compressible fluid, all we need to do is multiply these terms by density. As the density changes, that'll multiplying that times our area times our velocity will get us a generalized formula for the velocity at any 2 points, taking into account density times cross-sectional area. Hey there, kiddos. Today we're going to learn how hoses work. So I have right here a standard variety garden hose, and obviously the input of the water is on one end of the hose, and then the output is right here. And as it comes out of this opening has some area to it, right? Looks like it's a couple of centimeters in diameter, so we can find the area for this opening. However, much like most physics concepts, you have an intuitive grasp of how we can increase the velocity of the water coming out of the hose, right? So when I turn this on, the water is going to come out with some velocity while the opening is this area. However, once we close over that opening and reduce the area of the opening where the water's coming out, that's going to change the velocity of the water coming out of that opening, right? And it's going to change it relative to that equation, A1V1 equals A2V2. So you probably already know what's going to happen when I cover over this opening with my thumb, whether it's going to increase in speed or decrease in speed. So let's do that. All right, so when the entire opening of the end of this hole is open, then the water is going to come through at this rate, right? This velocity. And again, we have a certain volume of water that's moving through per unit of time. However, since that same volume of water is going to continue passing through per unit time, if I take and cover over this opening, we're going to have to increase that velocity of that water so the exact same volume of water continues moving through at the same per unit time. However, now there's less of an opening, less area for it to move through, the speed of that water increases. Isn't that cool? All right, let's play around some numbers having to do with our garden hose. So let's say that the nozzle we're going to put onto a garden hose has a radius of 0.025 centimeters. And the radius of the garden hose itself, the opening of the garden hose, is 0.9 centimeters. So I'm going to call the garden hose itself radius 1. So that would be 0.009 meters. And radius 2 for the nozzle is 0.0025 meters, or 0.25 centimeters. The flow rate through the system will again be the same no matter whether the volume of fluid is moving through the hose or through the nozzle. And so that'll be 0.5 liters per second. So our volume per time equals 0.5 liters per second. And again, since we know that every 1 liter is 0.001 cubic meter, we can express this in terms of cubic meters per second, and that would be 0.0005 cubic meters per second. So basically what this looks like, right, is we have a hose, and that hose has an opening, but then most hoses, if we put a nozzle onto it, then the nozzle is going to have a different opening, right? So the tube of the hose has radius 1, but the tube of the nozzle has radius 2. So obviously, even though the particles of water in the hose are going to have some velocity coming out of the nozzle, they're going to have a larger velocity because the nozzle has a smaller area. All right. So let's figure out the speed of the water in the hose itself. So as we move through the hose, again, the the volume over time will equal the cross-sectional area of the tube they're moving through times the velocity of the individual particles within that tube, right? So if we want to take and find our velocity is going to be our v over t, right? Our flow rate divided by the area of that tube. So in the hose, our area is defined by our radius, which is 0.009 meters. So let's take and let's convert that into the radius into area. So our area is pi r squared for r1. We're plugging some numbers over here. We got 0.0005 cubic meters per second is our volume flow rate. And we're going to take pi times our radius is 0.009 meters, and we will square that. And that will give us a velocity for the hose of about 1.96 meters per second. Cool. But then that fluid, that water is not going to stop in the hose, right? It's going to keep going through that nozzle, but that nozzle has a much smaller area to it. So we can find our velocity for the nozzle by taking that flow rate, which will be the same in the nozzle as is in the hose, and divide that by the area of the nozzle. So this will be our volume flow rate divided by pi times the radius of the nozzle squared. So that'll be 0.0005 meters cubed per second divided by 0.0025 meters squared times pi. And that'll get us a volume over the nozzle of about 25.5 meters per second. So again, this is why we attach nozzles to hoses, right? And we could do the same thing with your thumb over the opening of a hose. But if we restrict that area through which the volume of water is flowing, then we get a much larger velocity as we decrease that area. So velocity goes up when area goes down. Cool. All right. So we're going to take, and in class, we're going to explore a little bit more about volume flow rate.